Okay. Well, hi everyone. This is Sidi Najee, and I would like to make sure that I show you the equipment associated with this experiment, which we're trying to verify Newton's second law. The equipment that we need is, in this case, a stand where you would be able to attach a force probe. The force probe setup should be at 10 Newton. There's a little knob here that deals with that. Then, of course, the force probes needs to be connected to the logger probe here. And then we've got a motion detector. And then that is also attached to the logger probe. And the logger probe unit is connected to the laptop right here, where we're going to do, our measurements and an analysis. Of course, a calculator handy, that would be good. And then you need a spring, and then you need some kind of a mass of some sort. And in this case, what we're going to be trying to do is, we're going to try to cause this mass to be oscillating in a spring, and at the same time we're recording the amount of force that that object is applying on the spring in its up and down motion, and at the same time the motion detector is capturing the position, the velocity, and the acceleration of that hanging object. So I'd like to show you how we're going to start the whole thing. So the first thing you would like to do is you would like to hang this right here, okay? And then you make sure that the line up with the force probe is reasonable, okay? Then after that, what you should do at this point is you fire logger probe. In my case here, it's already fired, and you could see a sample of the graphs that you would be getting. But I'm going to do it as if we're doing a brand new thing. So in this case, when you do this, automatically you should be able to notice that there will be three. I don't know if it's clear, in the camera or not, but you should be able to see a force graph versus time, and a position versus time graph, and a velocity versus time graph. The first thing you would like to do in this case is to go next to the axis, the y-axis for the position, and you click on that and you change it onto a velocity. And then you go to the velocity, and which is the third graph down, and you would like on the Y, you click and there's a drop menu, and you would like to select acceleration. So what we'd like, in other words, to graph here is the force, the velocity, and the acceleration. And what we're trying to figure out here is the force going to be directly proportional to the velocity, or is it going to be directly proportional to the acceleration? Okay, so that's what we are trying to verify in this case. Of course, the first thing we're going to do is we're going to zero everything. That way, we would not have to worry about the current configuration. By zeroing this, we would be able to tell both units that these are the zero conditions. So at this point, I'm going to move here, and I'm going to zero this right there. It's going to ask you, it's going to have a pop-up window, as you can see right there, and it's going to ask you if you want to zero both of them, and you should confirm that. Yes, indeed, that's what we would like to do. Once you have that, then at that point you head up to the green button up here at the very top. I don't know if you can see it or not. And what you do at this point, you just gently raise this like that, and you let go. Now, as this is oscillating up and down, and once it establishes, a little bit of a rhythm there, you go back to the green button on your Logger Pro software, and you click that. And then you would hope that you would start getting some interesting thing like that. I hope you can see some of it on the screen there. And you let it run until it runs its course. Now it's done. Okay. Now you stop this and you relieve, the mass from its. By the way, when you are pulling this, be gentle to not pull it too hard or compress it too hard, because you don't want the mass to fall on the motion detector there. Now at this point that you got this, let me see if I can get this a little bit darker here, so we would be able to see a little bit more of the screen there. So I'm going to darken this a little more so you would be able to see a little bit more of the computer screen there. Okay, so at this point, what you would like to do is you would like to go right here, you know, to the, not to the middle, but to a portion of the graph. And then what you do, you would like to drag like this, you know, to a reasonable amount of peaks and valleys. And you stop right there. Now, when you do that selection, you must understand that an equivalent selection is also made for the velocity and the acceleration. And before you do anything else, it would be really cool for you to just look at it and see which of the two graphs, the red and the other two blue ones, which ones are going in tandem with one another. Is it the force going in tandem with the velocity, or is it the force going in tandem with the acceleration? Meaning the peaks match, or the peaks and troughs seem to be matching. From that, you should be able already to have some qualitative idea of which, you know, whether the force is directly proportional to the velocity or the acceleration. But here's the beauty now. We're going to go into the nitty-gritty quantitative stuff. So at this point, what we would like to do is we would like to go to the curve fit icon, and we're going to click that. When we click on that, of course, this is a sinusoidal, it looks like a sine wave type of thing. So we're going to look for a sine, you know, curve fit, and then we're going to say try the fit. When we do that, and we confirm that, we say, okay, notice here, a new window is going to show up. We're going to move it a little bit out of the way so it would not be on our way there. And then at this point, pay attention, you know, to those numbers, and we're going to come back to them a little bit later. Now, without changing anything, just scroll down, and not scroll down, but rather bring your cursor down until it becomes a hand on top of the second graph. Just click and don't do anything else and ask for yet another curve fit. So now we're going to do curve fit for the same portion that we selected for the force, but we're going to do it for the velocity. And the try fit should be already set on the, on the sine curve. So at that point, try fit, and then say okay, and then grab that and move it a little bit out of the way. And then bring your cursor down a little bit until it becomes a little hand. You click on that, and then at that point, don't do anything, and you just click on the curve fit once more, and then at that point, say try fit one more, and then you should be able to get some numbers, and then you would do that. What I would like you to take a look here, there are two major numbers that I'd like you to pay attention to. I would like you to record down the amplitude value, meaning the A according to each one of the graphs. So record the A for the force, the A for the velocity, and the A for the acceleration. So those are the first numbers that I'd like you to record. And then the second set of numbers that I'd like you to record are the B values. So, oh, excellent timing. This is the call for prayer. So I'm supposed to be praying, you know, the afternoon prayer, but I'm going to have to wait, and I'll do it at home. Thank you. I'll mute it for the time being. Okay, so here we go. So at this point, my friends, what I'd like to do at this point is you record the B values, and once you do that, then the cool thing starts. Now, if Newton's law is accurate and F is equal to ma, in order for us to obtain the value of the mass that's being, you know, oscillated up and down, we would have to do force divided by acceleration. Of course, if Newton's law is not valid and instead it's F equals mv, for instance, when we divide the F by the v value, then we would be obtaining some, you know, value that is related to the mass somehow. But of course, if it's wrong, which we expect to be, then we're going to get that. So here we go, my friends. At this point, I am finding the A value for the force in this case is 1.273, and I am going to divide it by, of course, these values are the amplitude values that you just recorded, okay? And I'm going to divide it by the value of the acceleration, which is 2.411. Okay, so divided by 2.411, I get 0.5279, blah, 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 blah. 0.5279 9, etc., that is kilogram. So how many grams is that? Well, roughly, it would be 528.0 because of the 99. So that's the value roughly that we're getting for the mass according to this. When we look underneath this, okay, we see that the value of this, upside down, okay, cool. We see that the value is 505.9. Oh, okay. So at that point, we're going to compare this value with 500, what again? 505.9, and just to see the difference between the two. And then we divide that by the real value, which we measured 505.9. And the answer that we get, we multiply by 100 to figure out what's the percent difference between the two values to see how close they are. And my friends, we get 4.368%. What do you think? Cool or no cool? Now, if you try to do the same thing, obviously, with the velocity, you're going to have 528, okay, minus, and according to the velocity, the velocity value, you are having 0.3420, 0.3420, which means we're doing what the amplitude of the force, which is 1.273 in my case, of course, and then divided by 0.3420, hit enter, I get 3.72 kilograms. There's no way that this is a 3.7 kilogram deal. My friends, Newton is definitely a cool guy in the whole process. A cool. Thank you.